Right, so welcome to the third phase of our data science and data analysis questions for data scientists and data analysts looking to ace their next interview and land their dream job. So, in this phase, we are going to be looking at statistics and probability for data analysis. So, if you made it to this phase three, then we are super proud of you. And if you have not actually watched the tutorial for the phase one and phase two, I would suggest you actually go back and watch the tutorial of phase one and phase two before you head to phase three. Now, let's get started. So, the first question we have here is, what is central limit theorem? Now, before we go ahead to explaining what central limit theorem is, I want us to take a look at population and sample, because the central limit theorem has to do with sampling distribution of the mean. Now, when we are talking about population, what is population? One thing you need to understand is that population is the group in which a sampling is drawn from. So, population simply means the total number of members in a specific group, okay, or region. Now, when we are talking about sample, what is a sample? A sample simply means a small group of members selected out of the population. Some scholars have also defined sample as a snapshot of the population. Now, when you're talking about central limit theorem, you need to understand that this central limit theorem is one of the most important concepts in statistics, and it actually has to deal with sampling distribution of means. Now, for example, let's look at this image here. Now, when you look at this whiteboard, you will actually see that we have two diagrams showing sample and population. Now, when you look at this here, this is what we call the population. The population is the entire number of members in a given group or region. As you can see, this actually shows the entire number of members in this given group. And this is what we call the population. Now, when we are talking about sample, sample is just like a small fragment of the population. So, as you can see, this is just like a small fragment of the population, and this is what we call population and sample. Now, we have various sampling techniques, but the most used sampling technique is the random sampling technique. And when we talk about a random sampling technique, we talk about a situation whereby each member in this population is actually given equal chance of being selected. Members in this population are just picked randomly without actually giving preference to any of the members. So each member in this population actually stands equal chances of being selected to be a part of the sample. Now, what is central limit theorem? Central limit theorem states that as we continue to increase the size of our sample means approaches a normal distribution. Now, when we are talking about a normal distribution, it simply means a distribution that is not skewed. Now, you need to know that a distribution can be skewed to the left or skewed to the right. Now, in doing analysis, we actually use various methods to actually know if a distribution is skewed. We can actually use visual representation or statistical method to know if our distribution is skewed. Okay. Now, center limit theorem is telling us that the more we increase the size of our sample using random sampling, that our sample means will actually approach to a normal distribution. And one thing you need to understand is that the sample size should be greater than 30. Now, let's say we actually have this. Now, let's make use of this diagram. Now, let's say we have this here as our population. So let's say we took this as our sample A, then we have this as our sample B, then we have this again as our sample C, and we have this again as our sample D. Now, the central limit theorem is trying to tell us that the more we increase our sample size, the more the means of our sample approaches a normal distribution. Like I mentioned, one thing you need to know is that this theorem is only true when the sample size is greater than 30. So this simply means that as we increase the sample size from 30 to 40 to 50 to 60 to 70 to 80 to 90 to 100, the graph of our sample means will lead to a normal distribution. Now, this is what central limit theorem is all about. Now, let's go ahead and look at the answer that we gave. Now, in this answer, we said the central limit theorem says that regardless of the original population distribution, the sampling distribution of the sample mean approaches a normal distribution as the sample size increases. Like I mentioned, the sample size needs to be greater or equal to 30 to be sufficient. This property enables statistical inference such as confidence intervals and hypothesis testing. Now, this is actually a way you can actually explain during your interview section what CLT, central limit theorem, means. Question 2. When would you not use CLT for hypothesis testing? Provide a real world example. When would you not use CLT for hypothesis testing? Provide a real world example. Now, before we go into stating when we would not use CLT for our hypothesis testing, let's go ahead and know what hypothesis is. Now, you must have been hearing this word hypothesis, 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 even during your research or even during your project building in school. Now, the question is, what is hypothesis? One thing you need to know is that hypothesis is a prediction or a tentative answer to a research question. Hypothesis is a tentative answer to a research question. And when we say tentative, what does this mean? Tentative simply means that the answer has not been fixed or neither has it been verified. So it is just tentative. It is a prediction or a tentative answer to our research question. Now, you need to understand that we have two types of hypothesis. We have two types of hypothesis. When we talk about hypothesis, we have two major types of hypothesis. Let's go to our whiteboard. So, hypothesis is just a tentative answer to our research question. Now, when we talk about hypothesis, you need to know that in statistics, we actually have two major types of hypothesis. Now, number one, we have the null hypothesis, which is also represented as HO. Now, what is null hypothesis? Null hypothesis is a statement that there is no significant relationship between variables. And the second type of hypothesis we have is the alternative hypothesis, which is represented with H1. Now, the alternative hypothesis H1 is a statement that there is a significant effect on the relationship between the variables. Why the null hypothesis says that there is no significant relationship between the variables. The alternative hypothesis says that there is a significant effect or a significant relationship between the variables. So now the question says, when will you not use TLT for hypothesis testing? One thing you need to understand is that CLT works with random sampling. CLT works with random sampling. So you use CLT for your hypothesis testing when the samples of the population would be collected using random sampling. When the samples of the population would be given equal chance of being selected, which we call the random sampling, this is when you actually use CLT. Secondly, the next thing to consider before choosing to use CLT for your hypothesis testing is the sample size of your population. So when using CLT, you need to consider your population size because your population size will determine your sample size. So you need to ensure that you are working with a large population that will also result in giving you a large sample size. And remember, when we were explaining what CLT means, we said that CLT holds that the sample size should be greater or equal to 30. Thirdly, you can also use CLT for your hypothesis testing when your data is not heavily skewed. Now, let's go ahead and look at the answer for this question. So you can go ahead and say CLT should not be used for hypothesis testing when the sample size is too small, when the data is highly skewed, and when the samples of the population is not collected using random sampling. Now, let's go ahead and give a real world example. We said, imagine you are analyzing hospital readmission rates for a rare disease. If you have only 10 patients' data, the sample is too small and may not follow a normal distribution. Instead of using CLT based hypothesis testing, a non parametric test like the Wilcoxon side rank test would be more appropriate. Question 3. Explain bias trade-off concepts using K nearest neighbor as an example. How does it relate to overfitting? Now, the first thing we need to explain is what is K nearest neighbor? K nearest neighbor, also called KNN, is a non-parametric algorithm that makes predictions based on majority class or average of the K nearest neighbors. Now, one thing you need to understand is that when K is small, that means when K is equals to 1, the model has a low bias. Why? Because it closely fits the training data. Now, when a model closely fits the training data, it simply means that each nearest neighbor is closer to itself. It simply means that each point nearest neighbor is itself. Now, what happens when the model closely fits its training data? When the model closely fits its training data, it captures all the details of the data, including noise. Now, when the model captures every detail of the data, including noise, this leads to a high variance because a small change in the data leads to a drastic change in the decision boundaries. Now, in this situation, the model is able to predict on the original data. But when a new data is introduced, the model will not be able to generalize properly. And this is what we call overfitting. When a model closely fits its data, that it captures noise, and when a new data is introduced to the model, it will not be able to make predict accurate predictions, or it will not be able to generalize well. This is what we call overfitting. Now, let's talk about the large K. When K is large, for example, let's say K is equals to 100 in a data set of 1000 points. In this situation, the predictions will be based on a larger number of neighbors, which reduces the variance because the model will be less affected by individual noise points. But in this situation, the model can actually end up oversimplifying and miss important patterns in the data, which leads to underfitting. So what you need to understand is that when K is small, this leads to overfitting because the model understands every details in the training data and also captures noise in this process. But when K is large, it simply means that the model has a smaller variance and is less affected by individual noise points, but this can also make the model to oversimplify and miss important patterns in the data, which leads to underfitting. Now, what is bias variance trade-off? When we talk about bias variance trade-off, this is a situation where we have to choose between the small k, which means low bias, high variance, and overfitting, and the large k, which means high bias, low variance, and underfitting. In this situation, we are trying to balance the two errors between the small k and the large K in order to minimize the total error. Now, how does this relate to overfitting? When a model learns its training data too well, including noise, it harms the performance of new data. In this situation, when a model is introduced to a new data that is not the training data, the performance of the model will be harmed because it will not be able to generalize on the new data set. This is what leads to overfitting. And kindly note that in the situation of overfitting in KNN, small k leads to overfitting. Now let's go ahead and look at the answer to this question. Bias trade-off refers to the balance between bias, error due to overly simple models, and variance, error due to overly complex models. In k-nearest neighbor, a small k, example k equals to 1, leads to low bias but high variance, meaning the model captures noise and overfits. A large K, for example, K equals to 50, results in bias but low variance, meaning the model oversimplifies patterns and underfits. Overfitting occurs when K is too small, causing the model to memorize training data instead of generalizing well to new data. Question 4. When a p-value of 0.03 is observed, what does this mean? And how will you explain this to a non-technical stakeholder? Now, to answer this question, let's take a look at what p-value really means. P-value also means probability value, and it is anywhere between 0 to 1. So it simply means that p-value can be 0.03, it can be 0.02, or it can be 0.05. Now, what is p-value or what is probability value? Probability value is a statistical measure that helps us to determine whether the results of a hypothesis test are statistically significant. A low p-value, that is when p-value is less than 0.05, it shows a strong evidence against the null hypothesis, which simply means that result is statistically significant. However, when a high p-value is observed, that means when p-value is greater than 0.05, it shows a weak evidence against the null hypothesis, which simply means that we fail to reject it. Now, let's give an example. Let's say a company wants to know if a new marketing strategy increases sales. Our null hypothesis, which is HO, would say the new strategy does not increase sales, while our alternative hypothesis, which is H1, would say the new strategy increases sales. Now, when we have a p-value of 0.03, it shows a strong evidence against the null hypothesis. So, we would have to reject the null hypothesis. Now, what does this mean? This simply means that there is only 2% chance that the increase in sale is by chance. So, this simply means that the marketing strategy was effective in increasing sales. Now, let's go ahead and look at the answer to this question number 4. P-value of 0.03 means that there is a 3% chance of observing the given data or something more extreme if the null hypothesis were true. For a non-technical stakeholder, there is a 3% probability that our results happen by random chance. Since this is below 5% threshold, we have enough evidence to suggest that there is a real effect on difference. Question number 5. What is Bayesian versus frequency statistics? Now, when we talk about the frequencies and Bayesian statistics approach, you need to know that these are two major and important approaches in statistics. While the frequencies approach assigns probabilities to data, not to hypotheses, the Bayesian approach assigns probabilities to hypotheses. Secondly, the Bayesian models incorporate previous knowledge into the analysis, updating hypothesis probabilities as more data become available. Why the frequencies approach believe that the probability is a long run frequency. It doesn't incorporate previous belief. It only relies on current data. Now, let's give an example. An example of the frequencies approach of statistics would be if a factory wants to know if a new machine is efficient. The frequencies approach will test this machine's efficiency using a large number of trials And for each trial, they would check the statistical significance without considering the past trials or the past data. One thing you also need to understand is that the frequency statistical approach requires a large number of data, and they also make use of simple hypothesis testing like the A/B testing and p-value. But for Bayesian statistical approach, it makes use of a small data set and it requires continuous learning. An example of this would be our machine learning. Now, let's go ahead and look for the answer that was provided. Frequency statistics views probability as the long-run frequency of events. It does not incorporate previous beliefs, only uses data from current experiments. Example, a 95% confidence interval means that if we repeated the experiment many times, 95% of the intervals would contain the true value. Bayesian statistics. It views probability as a degree of belief, which is updated with new evidence. It uses Bayes' theorem to combine previous knowledge with observed data. For example, if testing a new drug, Bayesian analysis updates the probability of effectiveness based on previous studies and new trial results. While Bayesian methods allow the incorporation of previous knowledge, frequencies methods only rely on data from repeated experiments. Question number 6. When would you use chi-square test instead of a t-test? Now, one thing you need to understand is that chi-square, also called S-squared test, both chi-square and t-test are statistical tests that are used for testing relationships. While chi-square is a statistical test that tests the relationship between categorical variables, the t-test is a statistical test that compares the means of numerical data between two groups. One thing you need to understand is that a chi-square makes use of data type like no and yes, male and female, etc. Now, this chi-square tries to check if there is a significant association between two categorical data groups. The t-test makes use of data type like our continuous data, like the height, the weight, etc. Now, let's go ahead and check the answer. When to use each test? Chi-square test. Chi-square test is used for categorical variables. Example, yes, no, red, blue, green. It determines if there is an association between two categorical variables. For example, checking if gender male or female is related to preference for a product, like/dislike. T-test. A t-test is used for continuous numerical data. Example, height, weight, revenue. It compares the means of two groups. Example, comparing the average test scores of two different teaching methods. So, what are the major differences between a chi-square test and a t-test? A chi-square tests the relationship between two categorical groups, while a t-test compares the means of continuous data. Question number 7. What is correlation versus covariance? Now, what is covariance? Covariance tells us if two variables are positively or inversely related. Covariance simply tells us if two variables are moving in the same direction. But when we talk about correlation, correlation is trying to know if there is a relationship between the two variables. Now, while covariance indicates the direction of the linear relationship between two variables and how they vary, correlation measures both the strength and direction of the linear relationship between two variables. One thing you need to know is that covariance measures how variables change together, while correlation measures how strongly they are related. You must have come across when performing your data analysis, you would use a heat map to actually know how each variable in your data sets are related. Additionally, you need to understand that covariance shows us how two variables differ, while correlation shows us how two variables are related. Now, let's go ahead and check the answer. Covariance measures how two variables change together. A positive covariance means both variables move in the same direction. A negative covariance means they move in opposite direction. Correlation. Correlation is a standardized version of covariance that scales values between -1 and 1. A correlation of +1 means a perfect positive relationship. A correlation of -1 means a perfect negative relationship. A correlation of 0 means no relationship. So, what are the key differences? Covariance gives the direction but not the standardized measure of strength. Correlation normalizes covariance, making it easier to compare across datasets. Question number 8. What is the difference between probability and odds? Now, what is probability? When we talk about probability, we said that probability tells us the likelihood of an event happening as a fraction of all the possible outcomes. Now, probability is calculated as the total number of favorable outcomes divided by the total number of outcomes. One thing you need to understand is that probability is usually expressed as a percentage, while odds can be expressed as a ratio, a fraction, or decimal. So, This simply means that the probability that an event will occur is the fraction of times you expect to see that event in many trials. Now, what is odds? Odds represents the number of favorable outcomes to unfavorable outcomes. The odds are defined as the probability that the event will occur divided by the probability that the event will not occur. Odds is calculated using the formula the total of unfavorable outcomes. Odds is calculated using the formula the total number of favorable outcomes divided by the total number of unfavorable outcomes. Now let's go ahead and check the answer. Probability quantifies the likelihood of an event happening as a fraction of all possible outcomes. Probability is calculated with the formula total number of favorable outcomes divided by the total number of outcomes. Odds represents the number of favorable outcomes as against the number of unfavorable outcomes. Odds can be calculated using the formula the total number of favorable outcomes divided by the total number of unfavorable outcomes. Question number 7. Explain the difference between type 1 and type 2 error. Now, one thing you need to understand is that type 1 and type 2 error occurs during hypothesis testing. A type 1 error is a situation where we reject a null hypothesis instead of accepting it. In in type 1 error, we conclude that there is an effect when there is no effect, and this error is represented by alpha. In type 1 error, we a null hypothesis when we are supposed to accept it. Now, what is type 2 error? Type 2 error is accepting or failing to reject a null hypothesis. In this situation, we accept that there is no effect when there is actually an effect, and this is represented by beta. We can simply say that a type 1 error occurs when we incorrectly reject a true null hypothesis, while a type 2 error occurs when we fail to reject a false null hypothesis. Now let's check the answer. Type 1 error, false positive, rejecting a true null hypothesis, concluding that there is an effect when there actually isn't, represented by alpha, the significance level. Example, a medical test incorrectly detects a disease in a healthy person. A court case where an innocent person is wrongly convicted. Type 2 error, false negative, failing to reject a false null hypothesis, concluding there is no effect when there actually is. Symbol represented by beta, related to statistical power. Example, A medical test fails to detect a disease in a sick person. A court case where a guilty person is wrongly acquitted. Question number 9. How would you verify if a data set follows a normal distribution? So there are various ways to verify if a data set follows a normal distribution. We can verify using visual impression. For example, we can plot a histogram or we can plot a box plot. Plotting a histogram shows us if a data set follows a normal distribution, because using a histogram we can actually determine if our data set is skewed or not. Now, plotting a box plot helps us to know if our data set contains outliers. Now, a data set that contains outliers is definitely skewed. This is actually how we can use visuals to actually determine if our data set follows a normal distribution. We can also use statistical methods or statistical tests to actually verify if our data set follows a normal distribution. Now let's check the answer. Answer: visual inspection, statistical tests for normality. Now, we have various statistical tests we can actually perform to determine if our distribution follows a normal, to determine if our data set follows a normal distribution. For example, we have the skewness and kurtosis test, we have the Shapiro-Wilk test, and we have the Kolmogorov-Smirnov, which is called the KS test. So these are various tests we can actually carry out to determine if our data set follows a normal distribution or not. The last question we have on our list for the statistics and probability for data analysis interview questions is: differentiate between descriptive statistics and inferential statistics. Now, when we talk about descriptive statistics, descriptive statistics summarizes and describes the characteristics of a data set to its key features. Descriptive statistics provides a clear picture of what has happened in the data set within without making predictions. Common measures of descriptive statistics includes the central tendency. Includes the measure of central tendency, which we have our mean, mode, and median. We also have our measure of dispersion, where we have our variance and our standard deviation. Inferential statistics, on the other hand, uses a sample of the data set to make predictions and generalize insights on the entire data set. For example, we have our hypothesis testing using our t-test and our chi-square. For coming to the end of the statistics and probability for data analysis phase, which is the phase 3 of our top interview questions and answers for data professionals. See you in the phase 4, where we'll be looking at questions from data visualization and reporting.